Hi everyone and welcome to Physics with Mr. Simons. Right, we make physics simple and we get you exam ready, right? So today's lesson we're looking at electromagnetism, which is mainly a grade 11 question, right? And this comes from a grade 11 November 2015 exam question. And yeah, the key with this question is we give you area to calculate magnetic flux linkage. You see the other variations, we don't give you area, we can test area of a square, we can test area of a circle, etc. But let's look at the question. Alright, so question 10, the arrangements of apparatus to demonstrate Faraday's law of electromagnetic induction shown below. So we have a solenoid there with a whole bunch of coils or turns of wire around it. Here we're inserting a magnet, and there this here is a galvanometer, symbol for galvanometer, to show if there's deflection on that galvanometer, then we know there's voltage or induced current, right? So 10.1.1 state Faraday's law of electromagnetic induction in words for 2 marks. 10.1.2 state 2 ways in which the deflection on the galvanometer can be increased. So if you look there, we're working with a magnet and we're working with electrical wire that's turned around this coil. Alright. So either increasing or decreasing those, but I assume you still remember the theory your teacher taught you. Right, 10.2. A coil with area 0.6 meters squared. So you see the area is given is held with its axis coinciding with the direction of a magnetic field of strength 0.4 Tesla. Right. Calculate the magnetic flux linkage. So we want phi there for 3 marks. Then they say in order to produce an EMF of 9 volts, the area of the coil with its axis coinciding with the direction of a magnetic field is halved from 0.6 meters squared to 0.3 meters squared in 2 minutes. So we have a change in magnetic flux. Calculate the number of turns in the coil. So we're going to use the EMF equation, E equal to minus N, change in phi over change in T. Right, but without further ado, you can pause here, try to answer the questions, or you can just follow me and come back and reattempt it again, right? You have to get used to answering this. Pardon. State Faraday's law of electromagnetic induction in words. So the magnitude of the induced EMF in a conductor is equal to the rate of change of magnetic flux linkage, 2 marks. So magnitude of induced EMF, we induce EMF, so there wasn't voltage, we induce, we create voltage in a conductor by using magnetism. And that is equal to the rate of change of magnetic flux. So how quickly we change that magnetic field in relation to the electrical conducting wires I'm using. 10.1.2 state 2 ways in which the deflection on the galvanometer can be increased. So number 1, we move the magnet quickly inside the coil. So the faster we move the magnet in and out, the greater the deflection on the galvanometer, meaning we create a greater induced EMF. Or we can use a stronger magnet. We can also increase the number of turns in the around the coil. Right, now 10.2. A coil with area, so this question must be tested. It's just here we will change it. Coil with area of 0.6 meters squared is held with its axis coinciding with the direction of a magnetic field of strength 0.4 Tesla. Calculate the magnetic flux linkage. So phi equal B, which is my magnetic field strength, A for area, and cos theta, where the angle depends on what we're giving you. So my magnetic field strength is 0.4 Tesla. My area was given as 0.6 meters squared. And the axis is coinciding with the direction of the magnetic field, so therefore cos 0 degrees. Right, so 1 mark for correct formula, 1 mark for substituting correctly, and then last mark for getting 0.4 Weber. Alright, so cos 0 is 1, 0.4, or 4 times 6 is 24, so therefore 0.24. Take note, we can also say Teslas per meter squared. Alright, so that is how we calculate the magnetic flux linkage. Let's go to the next question. So we remember this one was 0.24 Weber. Next question is normally related to what we found already in the first one. In order to produce an EMF of 9 volts, the area of the coil, I assume you remember EMF stands for electromotive force. The area of a coil with its axis coinciding with the direction of a magnetic field is halved from 0,6 to 0,3. Right, so they want us to calculate the number of turns. So again, there's a change in area, so phi and area basically inversely proportional. If I halve the area, or not inversely, sorry, directly proportional, my apologies. If I halve the area, I'm basically halving phi. Remember what 0,6 phi was? 0,24. Right, so here, PA cos theta 0,4. My area is now 0,3, and we're still working with cos 0. Gives me 0,12 Weber. So as you can see, area got halved, therefore my magnetic flux also became half. Right, so EMF equal negative N times the change in phi over the change in T. The EMF, they said, is 9 volts. The change in magnetic flux, final, is 0,12, the final one after I changed, minus the initial, which was 0,24. The change in time, I assume you know there's 60 minutes or 60 seconds in a minute. So 2 minutes, 2 times 60 gives me 120. We simplify that, I have negative 0,001. 9 divided by that gives me 9,000 turns. So 1 mark there for calculating my new change in magnetic flux there. Calculating correct formula, correct substitution, correct answer. So I hope you see the bigger picture, you understand what I've done. Wish you nothing but the best. See you in the next lesson. God bless. Bye.